Hi everyone, in this session we will introduce our work, suppose convolution of CNN with compression sparse matrix multiplication flow in TVM. This work is joint work with Weiqi Lai, Yu Hong, and Chongwen Huang from Mediatek, and also advised by my thesis advisor Zheng Kun Li from PL Lab in National Tsinghua University, Taiwan. In this presentation, I will first introduce our work and its background. And we will introduce how we design to implement the flow for Sparse in TVMs. And then it's the experience and conclusion. As we know, deep learning is playing an important role in our life nowadays. So lots of developers try to exploit the technique of deep learning in edge devices. However, the resource and the overhead of models are always cost a lot. So many researchers tend to reduce the overheads of convolution by different implementations, such like image column plus general metric multiplications, or vinaigrette, or fast Fourier transformation. And our work try to build a general flow for different backends which target to sparse models to maximum performance. So for our implementations about FFT is more specific on GPU. And as for vinaigrette has to modify the structure of the whole models to better utilize the sparsity of Sparse NN. So our work selects image column plus GEMM to offer a more elastic and general flow to utilize the sparsity of Sparse NN model. Mentioned about sparse model, we call the CNN model is sparse if the weights of the model are highly sparse. And due to our work is based on sparse CNN, we collect sparse model from two different open sources. And we get ImageNet-based model from Sparse Zoo. And also we try to prune our CIFAR10 models by an open source distiller from Intel AI Lab. And distiller provides several pruners, so we can easily prune CNN models by retraining with the pruning schedule we define, just like the example showing here. And we have to declare which layer of weights we have to prune, and the desired sparsity, and which pruner we are going to use in the pruning schedules. So the main idea of the pruner is that we have to add the binary mask to the weights to match some elements in weights, and those elements are going to remain at 0 in the pruning step. On the other hand, the other elements will be modified during the retraining step and try to keep the correctness of the CNN models. So as for TVM, TVM is a deep learning framework that focuses on inference. And TVM supports models from various sources or formats like ONNX, MXNet, TensorFlow, or PyTorch. So TVM then converts model into two-level intermediate representations like relay IR and TIR. So the first one is relay IR. Model will be converted to a tree structure computation graph as relay and do some high-level optimization like OP fusions or data layout transformation. And then the second level will convert to TIR. And TIR separates the algorithms and how to execute the algorithms of an operator into two aspects. So it's more easily to decide a suitable schedule for different target backends. And it also provides more elasticity of our flow. And this is an overview of our flow. We will first prune the model to the sparse by the pruning tool or distiller. Then we take the sparse model as input into TVM. So when TVM turns model into relay IR graph, we decide the visitor to replace target convolution operator into an image column transform operator with a normal dense operator to do matrix multiplication. Then we exploit TVM existing paths to replace normal dense operator to sparse dense operator that supports compression scheme computation, and we can start to inference our model. So because TVM is not supporting image column plus GEMM flow now, so we have to create the new operator image column first. And here I will first introduce image column and GEMM. So in direct convolution, suppose we have a kernel map with size 3x3 and a feature map with size 6x6, and we set stride size as 3. And to do convolution operation, we need to do element-wise multiplication between kernel and the corresponding elements on the feature map. And then we have to sum solve the result to the output, like here, 9. And next step, we will move our kernel map by the stride size on the feature map. And we will do the same element-wise multiplication on the corresponding elements on feature map, and then sum solve to the output. So in here, we can see that in direct convolution, the element in feature size will not be accessed continuously. So there might be cause a lot of cache problems. And due to this reason, each column duplicates the elements which are going to multiply with kernel map each time, and then put them in continuously into transfer 2D matrix. And as for the kernel side, they will also transfer into a corresponding 2D matrix. And due to the Sparse model we use, so we can know that our transfer matrix at kernel side here will be highly sparse. So we could use some compression scheme to store this matrix. And to implement image column operator, we could first infer the new output shape by convolution existing attributes like padding size, dilation size, and stride size to get the new output shape. Then the transfer matrix shape of feature map could be also inferred by the kernel shape and the output shape we calculate. To utilize the sparsity at kernel matrix, we exploit compression format to store the matrix and try to prevent the unnecessary computation of zero value and to save some memory. So in here, I will briefly introduce two different compression formats that TVM has supported now. So the first one is compressed sparse raw CSR format. And CSR use 3 array data index and index pointer to store non-zero data. And as example shows, we could see that we need to start from which position in index array for first row. So in here, we have to start from the index 0 in first row. And we look up the index array here. So we can know there is a 9 in index 2 in first row. And here we have index 3 in first row have element 8. And as for BSR format, it is similar to CSR actually, where in BSR we need to compress the matrix size by selecting a block size first. So suppose we set block size as 2 times 2 here, and the new block matrix will be represented like the block matrix 3 times 2 size. And if there are no non-zero value in this block, we can not to store this block and remain as 0. Otherwise, we have to store all elements in the block matrix, like the A, B, C. We have to store some 0 elements in this block. Then we could exploit the CSR format on this block matrix to convert it to BSR format. And let's introduce our conversion flow. And in our conversion, we separate as 2 steps. And in first conversion, we will traverse the whole model and graph and find the target convolutions. And we decide to convert the convolution into image columns and the dense operator and the reshape operator or not by checking the sparsity threshold is high enough. And in the next conversion, we exploit TVM existing path called dense to sparse dense and try to convert a normal dense operator into a sparse dense operator, which is supporting metric multiplication in compression format. And also we convert the kernel weight in parameters to 2D matrix offline in order to directly use the conversion function over in SciPy in here to CSR and to BSR. And this is our experiment environment. And as for test model preparation, as we mentioned above, we get image net model by sparse rule, and we prune cisplatin models by this theorem. So we define two pruning every layer of convolution weights and select AGV pruner as our pruners. And we retrain the model for 100 epochs with 0.006 learning rate. And this is the influence between sparsity and accuracy of CFAR10-based models pruned by ourselves. So we can see there are only under 5% drop of accuracy when sparsity is under 90%. And as for 90% to 100% sparsity, because our pruning schedule is trying to pruning every layers of width, and some of the weights in the first few layers might be more sensitive to a computation result. So that might cause the lower accuracy when our sparsity is over than 90%. And as for the performance, we test both dense and sparse CNN model with our flow. And for the left chart of dense model, which the dense model is the sparsity of weights are all non-zero. And we can see that the blue one is the time the running with direct convolution, and the pink one is the time that running with our flow. So both of these versions are not adding any other optimization. So from this chart, we could know that we can get at most 4 times of speed up by our flow, even the model is dense. On the right-hand side, we can see the result of sparse model by exploiting the sparsity and compression metrics. We could save lots of computation and get the most 16.3 times of speed up by our flow when the model is sparse enough. So, okay, I will briefly conclude our work. So in our work, we first decided the flow for sparse CNN in TVM, and we implement the image column operator in TVM to support sparse convolution. And then we design a visitor to replace target convolution 2D to image column plus GEMM. And at last, by our flow, we could get at most 16.3 times of speed up compared with direct convolution, and both are without any TVM optimization. And thank you for your listening.